Hello, everyone. Thank you for coming. My name is Igor, and we will talk today about OCI hooks and how they are related to the Kubernetes world and to the container world in general. So yeah, first of all, who am I? I'm a principal software engineer working in Red Hat in the OpenShift virtualization group. And I'm also one of the core maintainers of the kubelet repository and the kubelet organization. So in the agenda today, we will take a snippet from the container history and how these components evolved, the modular approach. Then we'll do a quick overview on them, and then we do a deep dive into what OCI hooks are, how to use them, the drawbacks and possible alternatives. So yeah, let's begin. So the quick overview of the history, what I want to bring you here is that before Docker, it was kind of hard to use containers. So you have to know the OS specifications and the complex tooling in order to create the isolation silo for your application. And then at some point, Docker come with simplifying these complexities into some tooling, and they were also presenting the image format idea. So that basically allows you to do container redistribution. And then container explosion happens, the containers become widely used. And later on, companies expressed some concern. So the Open Containers Initiative was created back then, and also the CNCF formed. And fast forward for today, we can think of the core technology stack that allows you to run containers on your cloud, divided into three parts: container runtimes, engines, and orchestrators. So a few words about the Open Container Initiative. So the fragmentation that was before this specification was created lead to concern that if you have like multiple cloud providers and you have your application, so you would have to create, I don't know, 5, 6 different ways for packing your application and 5, 6 different ways for how to run it on each of the vertical solutions. So that vendor locking expressed, so that was the concern, and OCI was then created by, let's say, the market leaders, and OCI specification can now define, so using the OCI specification, you can now comply of how to run your application and how to pack it using the OCI runtime and the image specifications. So let's start talking about what container runtime is. So container runtime allows you, so is responsible for creating the isolation silo for running your application on the host. And it also allows you to insert or inject the required resources for your application into that silo and provide you with a way how to run the application inside the silo. So here is an example of how, if we take the OCI runtime specification, so with that specification, you can just, in a declarative manner, define how you would like your application to run inside the container, and the container runtime will just do what you define here. So for example, you can define the process you want to run in the container, the environment variable, the arguments. Also, one important thing that I wanted to show is that here in the root, you can define where your rootfs is. That means that the OCI runtime, it doesn't care about how the image format looks like. So you need to just provide the rootfs, prepare it ahead of time. And also the specification allows you to define how you would like your application to run on different operating systems. So for example, in Linux, the building blocks of the isolation are containers, are cgroups and namespaces. So here you can define which namespace you need for your container, and also cgroups you can define there. So I brought you an example of runc. Runc is one implementation of container runtime. And as you can see, runc as a container runtime, it doesn't, you need to provide it with the rootfs already, and you need to provide it with the spec. So here's an example that you pull the image, and then you create some default spec with runc, and then you can run the container. So basically, if you are an OCI compatible container runtime, so you need prepare for me what you want to run and how to run it, and then you need to launch it. So who is responsible for preparing all of this? So this will be the container engine. So the most important part in the container engine is that it allows you to manage the container lifecycle, like start, stop, pause, execute something inside the container. And it's also responsible for basically rendering that runtime specification file based on what you tell it to do. Like if you think about Docker or Podman, so when you do Docker or Podman run, and you put some mounts that you want to share with the host and the container, so the container engine will render it into the container specification file. And container engine also responsible for other things such as sophisticated network and storage setup for the container runtime. And it also tells how to run the process inside the container runtime specification. So here I brought you an example of CRI-O, which is one of the container engine implementations. It's very popular in the Kubernetes world. So using CRI-O, you can see that you have only one command to run. It's responsible for pulling the image. So basically, the container engine is responsible for managing the container registry pulling and pushing. So here we can see that you can run a container inside the pod, and pod is a container, let's say, container setbox. It's an abstraction that container engines are using in order to comply with the container orchestrators, like in Kubernetes, for example. Now let's talk a little bit about orchestrators. So what we saw until now is representation on a single node level, but what about the application lifecycle itself? What if you want to connect your application lifecycle into container lifecycle? What if you have like multiple containers for your application? Container orchestrator should answer these requirements, should help you to define your application state, and it should then interpret it into downstairs to the container engine and so on. So there are most popular is Kubernetes. There is also the Docker Swarm, but we will focus in our talk on Kubernetes. So basically, how Kubernetes connects or interfaces with this modular approach. Kubernetes has a plugin system by design. So there are different plugin systems like CSI, CNI, but we will talk about the CRI, which is the Container Runtime Interface. Container Runtime Interface is defined, it's an open source communication protocol. So if you are a container engine and you implement CRI API, so Kubernetes can use you. And if you are on the other way, container orchestrator, if you speak that language, that you can manage the application lifecycle through the container engine with that API. And kubelet is the heart of Kubernetes, so he talks to to the engine and the runtime levels. Here, a quick example of how it goes in Kubernetes. When you create your application YAML, it goes to the API server, and then it's scheduled on the node. And then kubelet receives an update that it needs to create a new container or new pod. And then it goes all the way down. These are gRPC methods that are being used in order to start up a container or a set of containers, depends on what is defined on the pod. And later on, it goes down to the OCI runtime. So you have already the config.json, and it launches the runtime with the configuration. So, and now we reach the OCI hooks. So we are going back down to the container runtimes. So OCI hooks are operating on that level. And they are basically allows you to customize or prepare resources for your application that cannot be prepared neither by the container engine or by the container runtime. We can think about like GPU. If the application needs some access to the kernel driver, to the GPU driver, and it needs some parameters to be passed, these parameters need to be calculated on runtime, and they cannot be calculated by the engine or by the config.json spec. So you had to use hooks. Also, using hooks, you can configure resources on the control groups level, on the cgroups level, when the runtime cannot do it. So hooks, like hooks, they have hooking points. And the hooking points are related to the container runtime, container lifecycle inside the container runtime. So you have 4 stages and 5 types of hooks. You have the pre-start stage. So this is the very beginning, before the isolation silo is being created. And then the second hook is just before the runtime doing chroot into the mount namespace of the container. The start container hook is a special one because this is the only hook that runs from inside the container context and not from the host context. All other hooks, when you run them, they see the whole picture. I mean, they are like privileged. They see the whole host, and then you can do some privileged setup for your container. Post-start and post-stop are pretty trivial. In post-start, you can do some logging, for example, if you need, and in post-stop, you can do some cleanup for the custom resources. So, a few more words about hooks. Hooks are defined in the OCI runtime specification, but they are basically optional. So the container runtime doesn't have to implement them. In order to use hooks, you need to put them in the OCI specification, in the file, and this is the format, so you can define as much hooks as you want per stage. And Kubernetes, the orchestrator level, or the CRI API, like we talked before, it doesn't have representation for hooks. So they need to be configured on the container engine level. So the container engine then renders the config.json, needs to render hooks into the config.json. And not all the container engines supported, and CRI-O does support. I just wanted to show you that since there is no high-level API for OCI hooks, this is the container engine API that allows you some degree of flexibility how to use the hooks, because maybe you want to use the hooks only on some conditions, not for every application that your container engine is creating. So the hook representation is the version of the OCI specification, the hook itself, and the interesting part is when. So basically, it can be either always, or if you have a match a regex match on some container metadata in the annotations, or the command, the execution command. So, for example, I took it from CRI-O. Here, the container engine will render the hook into the config JSON when it sees like the following annotation regex. And on the right side, when the container command includes like /init or /systemd, then CRI-O will render it into the OCI runtime specification. And now, how do I know all of that? It's because it comes handy in our project. So in KubeVirt, we run virtual machines inside pods. And we wanted the virtual machine pod to consume swap memory. And in Kubernetes, by default, swap memory is not allowed to be used by pods. I mean, we are working on it. It should be hopefully GA'd in the next releases, but we didn't want to use a beta feature, and we wanted to configure it by ourselves. So the easy part is that in order to allow your container to use swap memory, you just need to configure it in the container cgroup file, memory.swap. So we created an agent that looks like a diamond set, so it deployed like a diamond set. And what this agent does, it installs an OCI hook on each one of the worker nodes, and it installs the hook executable. So basically, when new pod is being scheduled, so kubelet talks to CRI-O via CRI API. CRI-O in turn reads the CRI API resource request, renders the config JSON for the OCI runtime, and then CRI-O sees that it needs to inject always the post-start hook. And with that way, each pod that is running on a node with the wasp-agent will be allowed to use swap. But there is something important to know about OCI hooks, is that, I don't know if you noticed, but it's intended for a stateless one-off operation, because if you think about it, how these OCI hooks are running by the container runtime, it just forks the process and calls the executable that you defined in the config JSON. So it basically cannot communicate with the upper layers and cannot communicate what it does. So if you think about this model, container engine doesn't know what the hook did, and neither the kubelet and Kubernetes. So they can also race with CRI-O itself, because when we use hooks for C groups, and that C group can be also touched by the container runtime itself later on, because you define something that you want in the config JSON. So the config JSON C group will override what the OCI hook did. So that's not that good. And also it's hard to debug, because the execution context, when this hook is being forked, it doesn't have any pipe of anything to the container runtime. So you had to do some I/O operations in your hook executable, which is also not preferable option, because the hook should work efficiently. It should not slow down the container lifecycle process. And last one is that when you run the OCI hook, if you need to gather some data about, I don't know, about the application, or about some special metadata about the pod, you don't have it. So the maximum that you have is what we saw in the CRI-O configuration in the when. So you can define annotations or commands, but inside the hook context, you don't know much about the pod. You only can know about the container specification. In some cases, it's not enough. So the alternative, I brought you here, and one alternative that I know of is NRI, which stands for Node Resource Interface. And simply speaking, it's just OCI hooks, but on the container engine level. And why basically this is better? Because the container engine, the container state that the container engine holds, you can hook every request from kubelet to NRI, and NRI can modify anything related to the container resource and send it back to the container engine. And then the container engine will not, it will be synced with what you want to do because of the gRPC protocol, because of the NRI API. So basically, what the language that NRI speaks with the CRI is the same CRI API. And you can think of it as that you can hook on every CRI API gRPC method. So you can say, I want to hook on pull image request, and you can do something. And not only, this is not the only advantage. Another advantage is that you can run the NRI plugin in a stateful manner. So you can actually run a separated stateful logic for your hook. Yeah, so to summarize, so I did a really quick overview of container history and basically how it all leads to this separation of container engine, container runtime, and container orchestrators. And I try to show you the practical implementation of each one of these layers. We talked about OCI hooks, the use cases, and drawbacks and tips. So, yeah, thank you. So, you have questions? Oh, thank you very much. Yeah.
There are also some hooks in Kubernetes itself. So these are totally different, or?
No, yeah, I hope that it won't confuse you. No, this is not the hooks that you are talking about. Kubernetes on the Kubernetes API. No, these are very low-level hooks, and they are intended to run in a privileged mode. So you can do some. One classical example is that if you want to run your pod. Sorry. The question was whether the hooks that I'm talking about, so to not to be confused with the Kubernetes hooks, because Kubernetes API helps also the ability to hook on a life cycle, but on the life cycle of the Kubernetes application, not the OCI the low-level hook. So, yeah. To build a proxy, sorry, to build a proxy between? So the question was whether we can use a proxy between the communication between the container engine and the container runtime, right? Was that the question? So there is no communication protocol between these two layers. The container engine, what it does, it forks the process. That's what I tried to show, that in order to run the container runtime, so the container runtime is not a stateful server that you can communicate with. A container runtime is a tool. So it's like, so what container engine usually does is just does OSCMD with like crun, runc, or kata, and this is how it communicates. So that's the problem. Sure.
Why have you decided to use the CRI-O instead of the NRI in your solution?
So why did I decide to use CRI-O instead of NRI? You mean why did we decide to use OCI hooks instead of using NRI?
If I understood correctly, the NRI can create OCI hooks, or did I misunderstand?
NRI is like OCI hooks, but it operates on the container engine level. So basically, you can configure your container engine to accept NRI plugins. What you do is that you install an NRI plugin on the host, okay? And the NRI plugin should have a gRPC server and a gRPC client, basically. Using the gRPC client, you tell the CRI, whether it's CRI-O on containerd, that hey, I'm here, I'm a plugin. So this way you register yourself to CRI-O, and when you register yourself, you tell which hook you want to operate on. So, for example, if you create a container using, so you have a create container request gRPC method in the CRI API, and as an NRI developer, you register yourself. You create a gRPC client from the NRI execution, and you send the gRPC to the CRI-O or containerd, and you say, "Hi, I'm a plugin, and please, each time that kubelet or any other orchestrator sends you create container request, please pass me this create container request, and I will return it to you." So it's kind of a proxy. Yes, exactly. Yes. Exactly, because, for example, with swap memory can be configured using CRI API, okay? But Kubernetes doesn't want it to happen. So what I can do is when a container being created, so a container create request is being sent from kubelet to CRI-O, then CRI-O can proxy it to me, and then I can set swap memory from like 0 from disable to some value. And that way I will kind of bypass kubelet and Kubernetes. It's also not perfect, because then kubelet doesn't know that I modified the swap memory resource, right? So it's better to be used for really custom solutions. Sure. Yeah. Okay. So from security, the question is from security perspective whether it's safe or not to use OCI hooks. So they are operate on privilege level, and you have to make sure that you know about which OCI hooks, about the OCI hooks that are installed on your host. So the question was, how do you register hooks to be injected? So I mentioned it. So CRI-O, for example, is a container engine that supports injecting hooks. And each time CRI-O needs to render the specification file, CRI-O goes to some predefined configuration directory, and then there you should put your configuration for the hook. Like what we saw when the struct of when, annotations, commands on the CRI-O level. So this is how you tell CRI-O, look, I want you to inject a hook for container, but maybe with some condition if that container has some annotation or command. Yeah. More questions? Oh, thank you.